Hello, everybody, and today you are going to talk about the non-linear static analysis and the pushover analysis. My name is Dr. Mustafa Mufid Qasim. I'm a postdoc in University of Science Malaysia and School of Civil Engineering. In this session, you are going to know how to develop a modeling using SAP2000 and using eTABS also for developing a capacity curve based on the pushover analysis. Let me highlight first what is the meaning of non-linear static analysis. Nonlinear static analysis is commonly referred to the pushover analysis, which is a method help for determining the ultimate load and the deflection of the capacity of the structure. You can know the ultimate load and the deflection capability of a structure. And also, the pushover analysis, as you know, is a static method which help to simplify the nonlinear technique which help to estimate the seismic structure deformation, the structural performance, the structural behavior, the seismic behavior of the structure under seismic loading and under lateral loading using static method. This static method is different than the dynamic method. You know the dynamic method, especially for the non-linear dynamic method like time history analysis method, which is more complicated topic, which is more complicated and computing effort to do a model for using time history analysis because it will require the supercomputers, it requires the ground motions and a lot of intensity measures and a lot of damage measures and a lot of engineering demand parameters. But today we are going to talk about the pushover analysis. The pushover analysis is commonly used. Is commonly used to evaluate the seismic capacity, as I say. It's commonly used to evaluate the dynamic, the behavior of the existing structure, which appears recently in many guidelines and many papers and many researchers which have in retrofitting as a seismic design. And it is more applicable. It is also more applicable for the low-rise building and mid-rise building rather than the high-rise building. The high-rise building it have a lot of complexity which need to go to dynamic analysis, not go to the static analysis. So let's go now and start modeling or start showing you the SAP2000 interface and how we can model together. Here we go. Here's the interface of the modeling. Okay, you can see the interface. We have the toolbar, we have the quick toolbar, we have the drawing toolbar, and this window is, I want to go to new model, click on new model. This is a new model, you will see a lot of options and templates. You can see we have the blank, grid, beam, 2D trusses, 3D trusses, 2D frames, 3D frames, wall, flat slab, shells, staircases, storage structures or water tank structures, underground concrete, which is related to the infrastructures and can be related to underground water tank, solid models like finite element or shell element, and pipes and plates. So in our case, we are going to talk about the 2D. Okay, 2D RC frame structure, portal structure. You can see the options here. We have bracing system, which is concentric. This is the concentric. We have eccentric. This is the eccentric. So in our case, we are going to go to the portal 2D frame structures. You will see here what we need to define the dimensions of the RC frame. What is the frame that we are going to use? Number of stories, I will take it 5. Number of bays, we need to take it, also I will take it 3. Story height, let's assume 3.2 meter. And the bay widths will be like a 4 meter with bay widths. So in this case, we define the number of stories, we define number of bays, we define the story height, we define the bay widths of the structure, and we click OK. So after this, after we assign the modeling for this building, we have 3D view and we have 2D view, 3D view window, and we have 2D view windows. You can see now all the options are activated. The toolbar is activated. The quick toolbar is activated. The quick drawing toolbars also is activated. So first of all, we need to define the material of the structure. We say the structure is a reinforced concrete building. So first thing you need to know is to define the material. Go to define materials, and we have by default 4000 psi, which is 4000 pound per inch square for the concrete, and we have A99F550, which is for the steel grade. Start with 4000 psi, change it by default to let's name it C25 megapascal, and the material grade I will name it like C25, and your weight per unit volume I will take it 24 kilonewton per meter cube, and the modulus of elasticity I need to change this because modulus of elasticity will be in megapascal. I need to change this to Newton millimeter because the unit of omega pascal is in Newton millimeter square, so change this to Newton millimeter square. As I say, how to calculate the modulus of elasticity? The modulus of elasticity can be calculated using this equation, 4700 multiply by the concrete strength, which is 25 megapascal in our case, square root 0.5. You will get the modulus of elasticity is 23,500 megapascal, and the specified concrete compressive strength will be 25, and the expected concrete compressive strength will be 25 megapascal. In this case, we define the material for the concrete, we define the modulus of elasticity, we define the weight per unit volume, we assign the 25 megapascal for the specified concrete strength, and the expected concrete strength will be the same, and click OK. Okay, now we need to go to the steel rebars. The steel rebars, I will keep it by default because it depends on your place, in your country, in your fabrications, steel structures, but make sure the modulus of elasticity is still 199 gigapascal or 200 gigapascal or 200,000 megapascal. So the material for the steel will have no issues to change. The concrete strength is changed, the material, okay. Now, after we define the material, we need to define the beams and the column section size. So the beams by default is F-sec1. Okay. And the column by default is F-sec1. So we need to define, after defining the material, we need to define the frame sections. Define section properties and frame sections here. We have to change this one to add new property, concrete, rectangular. Take like this one. I want to take the column square. I will name it like column C 40 times 40, and this one will be 0.4, and this one will be 0.4. So in this case, we have the column 40 centimeter by 40 centimeter dimension, and the material is C25 megapascal. Make sure concrete reinforcement. Make sure this is column. I will take the cover by, I will take here 12 diameter. I will take it like 4 by 4. This you need to calculate this by the reinforcement ratio. And this one, the diameter for the stirrups, it will be 10 millimeters, 0.3. So we define the column here 40 by 40 centimeter. We have 1, 2, 3, 4 rebars and 1, 2, 3, 4 rebars in the in 2 direction and in the 3 direction. So we define the column. Okay, secondly, we need to define the beams. Okay, let's go for the beam. The beam, I will take it like also beam. I will name it beam 40 times 30 maybe. Yeah, let's take it like this. I'll take the drop beam 0.4. The unit is kilonewton meter, so make sure it is in meter. And 0.3 the width. You can see now the drop beam is 40 centimeter, the height and the thickness, and the width is 30 centimeter. Also make sure the material is 25 megapascal, and you can change this to beam. Instead of column, change this to beam. The beam designed only for the flexural moment, flexural behavior. For column we define for the axial load, for the minor moment, for the major moment. So in our case, the beam is only for the M3, which is the major moment. You can change this to beam and click OK. So for this one, we have beam, we have, let me change this to column. Okay, let's see. Column. Okay, so we have column, we have beam. Click OK. Now we define the material. We have defined the material and we have defined the frame sections. Now we need to change the boundary conditions. You can see the frame building here. We have pin support. Right click on the joint, you will see that we have restraint in X and Y and Z. So we need to change this. Assign all the boundary conditions. Okay, assign the boundary conditions, the joint. Go to assign, go to joint, restraint, and click on fixed. You have fixed, we have pin, we have roller, we have none. For the fixed support, everything is restrained. See, I will click on it. See, the translation in X, which is 1, translation in 2, which is Y, translation in 3, which is Z, is restrained. Similarly, for the rotation about 1, which is X-axis, rotation about 2, which is Y-axis, and rotation about 3, which is Z-axis, is restrained. This is for fixed support. Change this to pin support. You will see that X direction, Y direction, Z direction is only restrained. For the roller, only the Z direction is restrained. And for the none, nothing is restrained. So in the building here, we are going to take the fast restraint support, which is a fixed. Okay, click on fixed. Make sure it is assigned. Apply. And okay, this is the support have been changed. Right click on the joint. You can see the restraint in 1, 2, 3 in translation and 1, 2, 3 in the rotation. So will be here's a fixed support for the columns at the basement of the building. So after defining the material, we have defined the material, we have defined the sections, we have defined the boundary conditions. Okay, but still here, right click, still the beam is not the beam as we defined. And click on the column, still have different section properties. So what you only need to do is select the beams, select all the beams, and go to option assign, frame sections, and click on beam. You will see now everything is changed to 40 times 30. The dimension we have 40 centimeter dropping beam with a width 30 centimeter width. Okay, similarly for the column, select all the columns and assign column. So we have beam and column have been assigned based on our design sections. Okay, if you go to the define section properties, frame section, I need to remove this, no need for this one. Delete property and click OK. So we now define the material, we define the sections, we assign the boundary conditions, we assign the columns and the beams. What else we need to do is to define the load pattern. You know that the building will carry gravity load and will carry lateral load, right? The gravity load will be like a dead load and live load. And the dead load could be the self weight of the building itself. It could be the partitions. What I say the partitions means the partitions means the walls could be masonry walls, could be brick wall, can be cement walls, and can be the tiles, can be the paint, the plastering. All this we can call it as a partitions, like a superimposed dead load. Okay, so go to define load pattern. Go to define load pattern. We have that load by itself, which is self weight. I need to change this to SIDL, which is the abbreviation of superimposed dead load, and change this one to super dead. Super dead, yeah, super dead. And add, what else? I need the live load. LL, okay, go to live, change, okay. So we define, now we define the load pattern for the dead load and live load. We need to assign them, right? Usually you assign them on the beams. Gravity load should be on the beams, right? So assign the beams or select the beam, assign, go to frame loads, go to distributed load, go to SIDL, make sure it's SIDL, type of load is force, gravity direction, you're correct, and take it 15 kilonewton per meter run as an assumption values. You'll see now the 15 kilonewton per meter run have been assigned to the structure. Okay, similarly, assign the beam again, assign the beam again, and put the frame load for the live load now. Go to the live load, change this force pattern to live load, take it 20 kilonewton for the uniform distributed dead load UDL, and click OK, apply can see now it is 20 kilonewton here, 20 kilonewton on the all floors level. If you right click, you will see the load for the SIDL pattern is 15, and for the live load pattern is 20. So we have assigned that load for the modeling for this frame structure, RC frame structures. So after we define the material, we define the section properties, we assign the boundary conditions, we assign the load pattern, we define the load pattern and assign the load pattern. Now we are going to assign something called a diaphragm system. What is a diaphragm? The diaphragm system is a relation between the horizontal element and the vertical element. When I say horizontal element in the 3D view, it is the floor, right? It's the slab of the building. In the 3D view, we have the slab system. The slab system will carry the gravity load, and this gravity load will be distributed to the vertical element, and the vertical element will distribute it to the foundations, right? However, the diaphragm will transmit the lateral load. The lateral load will come in the any plane direction for the floor and will transfer these lateral forces and distribute these lateral forces to the vertical element based on the tributary area carried by the vertical element and based on the stiffness of the vertical element. So that's why the diaphragm have several types. We have fixed diaphragm or rigid diaphragm, sorry. We have semi-rigid diaphragm and we have a flexible diaphragm. So we will assume, most of the building, we will assume it as a rigid diaphragm. So go to assign, join, constraint, define join constraint, choose a constraint type, we have diaphragm, okay? Add a new constraint. Diaphragm number 1, we have how many floors? 1, 2, 3, 4, 5 floors. So we need 5 diaphragms. Add a new diaphragm 2, diaphragm 3, diaphragm 4, and diaphragm 5. This one, okay. So we have 5 diaphragms. Each floor will take 1 diaphragm. So we'll assign in 2D frame. In 2D frame, the diaphragm is not the slab. The diaphragm is a joint which between the column and the beam, the connecting joint between the beam and the column, we'll consider it as a diaphragm joint. So this is the first floor. Assign. See the green spot here means that the diaphragm has been assigned. Diaphragm 2, diaphragm 3, diaphragm 4, and diaphragm 5. So we assign all the diaphragm system. You can right click, you can see the name constraint. Right click on the 4, 3, 2, and 1. So now we have defined the diaphragm system. We define the boundary condition as a fixed support. We assign the load pattern, that load and live load. We define the sections, beam and columns. We define the material as a concrete 25 megapascal. What else? What else? This is an important thing we need to know. We need to define the plastic hinges. What is the plastic hinges? The plastic hinge is the location of damage. You know, we are applying the pushover analysis or the non-static analysis. In order to know the capacity behavior of the structure, we need to know the performance. We need to know the dynamic or the static behavior under seismic event. So I need to know where the damage will happen, on the columns first or in the beams first. On the beams and columns together, how much the flexural or the crack could happen uh, at the first floor, second floor, in the whole building. So the plastic hinges, as you know, it is, you know, the curve, stress strain curve. The stress strain curve is started with elastic, linearly elastic. As is the linear elastic is changed to plastic. This is a plastic zone. We need to see how much this building can behave during the plastic zone before it collapse or before it partially collapse. So we need to define the plastic hinges. Go to define, section properties, and hinges properties. I need to add a new property called concrete column. the interacting between P, M2, M3. P means the axial load. M2 is a minor moment. M3 is a major moment. And we have another for the beams. The beam is major moment interacting moment M3 and name this beam. Okay, we define the plastic hinges, but we need now to assign the plastic hinges. Go to select, object type, properties, frame sections. I need to select the beams first. This is the beams have been selected. Assign, frame, hinges, go to beam, 0.1 relative distance. Why 0.1? Because the damage will never be occurred at the intersection joint. It will occur at this area, a bit away from the connections. It will be here, like a 0.1 unit, because the beam is a 1 unit, so it's a 0.1, and this one is 0.9. So it is 0.9. No, it's 0.9. So 0.1 and 0.9 have been assigned. So we assign the beams 0.1, 0.9 on the structures. And then we need to assign this for the columns. And click 0.1 and 0.9. So we have the plastic hinges now for the columns and for the beams on the structure. So after this, we need to define the load pattern for the lateral load. Define load pattern lateral. I will name this lateral load, and as others, and add a new load pattern. So we assign all the joint. I need to assign this joint. Assign frame loading or joint. I need to take this lateral load in which direction? In X direction, 1000 kilonewton, for example. You will see now it is 1000 kilonewton, right? So it is uniformly distributed load as a rectangular loading on the structure, and define. Now I need to define the load cases for the pushover analysis. In order to define the load cases, we need the first thing to add a new load case. The add a new load case will be like, the first case will be dead load and L, nonlinear. Changes to nonlinear and take this as a dead load. Add for the self weight only and click OK. Another load cases, add a new load case. We will name it as initial pushover analysis. Also change to nonlinear static. Continue the state from the dead load nonlinear, and I will change this to live load and change this to superimposed dead load. Okay, and click OK. And the third case is the final pushover analysis. Final POA. I'll name this lateral and nonlinear static. Take this at P delta. Continue from the initial POA and take this lateral load. Okay, so lateral load is the 1000 kilonewton that we have been assigned, and modify this one to displacement control and change this to multiple states so that we can know the states of the deformation shape of the building, and click OK and click OK. So in this case, we have defined everything that we need in this modeling. We define the material, we define the frame sections, we define the frame hinges, we assign the load, we assign the diaphragm, and we change the boundary conditions, as well as we define the load cases and we define the load patterns. So it is now time to make file. For example, I'll save as for this one. I will name it like pushover analysis modeling model frame. Okay. So I can run the analysis, analyze, set load courses to run, make sure this is run, and click run. We will wait until the analysis is finished. So the modeling, you can see now the deform shape. Go to show deform shape, go to the final pushover analysis and click apply. Okay, you can see the deform shape here now change. I need to move on. See the plastic hinges have been on the beams first, which is in the IO level, which is still safe, immediate occupancy level. If you go more, the beams will have between the immediate occupancy and the life safety. Now the columns have the immediate occupancy and the beams are in the life safety zone. Now we can move on. Life safety, the collapse will be yellow for the beams have been collapsed here. So the collapse was started on the beams before the column. So we have, this is the plastic hinges. It take us like 17 steps, 19, 20. Okay, so this is the cases that we need. Or you can go directly to this envelope maximum and click apply. You will see this is the plastic hinges. So we have damage in the column here. We have damage in all the beams in the second and third floor. Okay, now we need to know the display show static pushover curve. You can see here the pushover curve. This is the pushover curve. It's the relation between the base shear and the displacement, right? Okay. File, display table. You will see the displacement and the base shear. So we have 0.212 meter, which is 200 millimeter, and the base shear is 243 kilonewton. So you can export this value, display the current table. You can go to Excel, okay, and you can display in the Word. You can view. Okay, so we can change this to Excel, and you can convert this to Excel, to Excel sheet. So this is how to, and here's the scaling. So you know now the pushover analysis, how we can develop this one, the display show static pushover analysis. You can also know you can see if you want to, as an extra note for the SIDL, if I want to see the 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 axial force. Based on the axial force, you can see the moment 3, the moment, you can see the moment of the structure, as well as this is how you can model and how you can design. You can take the modeling for the columns and beam and design, and now we can see again the deform shape, the last deform shape, the final pushover analysis, final pushover analysis, and go step by step. Go to the maximum and step by step. Okay, thank you so much for listening and have a nice day. I hope this video will help you how to model 2D frame structure and develop the pushover analysis. You assign the plastic hinges and display the static pushover analysis and model and draw the curve in a proper way using any software that you need. Don't use the software for the drawing. Just extract the data from here. Okay, extract the data and draw it using Excel or Origin Pro or any software that you are familiar with. Thank you so much and have a nice day and goodbye.